What is an algorithm? An algorithm is a precise and concise set of instructions that guide you to solve a specific problem in a finite amount of time. This is the definition given to me by my university course. So yeah, I'm studying COMP108 whatever. It's algorithms and data structures. But issue is, right, I can't really show the university slides because that would be copyright infringement, I guess, or something. I don't know. Oh, I'm not gonna risk it. But what I can do is show this website, which is someone's notes based on the slides, which is quite handy. Now I do have the slides here, but you guys can't see them because my screen isn't showing it. So I can verify that the content here matches that on the slides, but otherwise I can still show it here. And what I will be doing is, where did Obsidian go? What I will be doing is putting my notes into Obsidian, and yes, because I should be, well, it'd be a good way to build up my knowledge base about algorithms and data structures. So launching Obsidian here. I think I closed it by accident, that's why. Right. Oh look, my graph. So I don't think I really have anything right now. In fact, what I should be doing is creating notes first. So let's go files, go to my source things, and here I can create notes on each lecture. So with the lectures, yeah, here. So I believe I can show this at least. So these are the lectures, right? I've got quite a few to go through. Lecture 1 is just introduction, but then lecture 2 is this, lecture 3 is this, lecture 4 is this, what's this, what. So what I've done in the past is I've taken notes based on like per lecture. Like I gave each lecture their own source note. So for example, lecture 22 here for COMP116, you can see here that we covered quite a lot of like stuff with like eigen stuff. You can see we covered like well first of all, like just notes like that I got from the lecture, right? Like a matrix that has an inverse called non-singular. So like, yeah, so non-singular and singular matrices. Another way to write the determinant, the eigenvalue problem. So you got eigenvalues, eigenvectors, the characteristic polynomial, the spectrum, the dominant eigenvalue, the spectral radius. This if something is symmetric and it's transpose, and then a bit of eigendecomposition with a diagonal matrix. We covered a lot in like less, like by the way, this is like a 50-minute lecture, 50. So like it's just a lot of content anyway. But I'll basically be doing that as a way of going through these. They seem to be in alphabetical order when they should be in order of last opened. I don't know when that changed. Files and links. Is it like an order thing, or was that a plugin I had installed? I hope not. Oh well. Whatever the case, let's create a new one now. So new note here, and this will be COMP108 lecture 2, because that's what I'm on right now. It's called pseudocode part 1. So I'd put that in the information here. So like title would be literally pseudocode part 1. My authors would be, I guess, just lecture's name, and then the dates that this was published. So it's like the date the lecture was on. Now I can't actually remember when this was, which is the downside of not doing this at the same time they come out. But here we go. There are dates here, thankfully. By the way, this module is very well organized, I must say, which is very nice. Makes it easier to review stuff. So this was the first, the 29th of January. So I hate how I can't reverse this, but whatever. 29th of January 2026. Tags, university lecture, IDs should be relevant. Have a link here. This is a link that I can access for now. I don't know. I don't know if I maintain access to that later, but whatever. Preview, have an image of the front slide. Screenshot. Shows my clipboard. So just paste it there. Don't know why that chose this one to go. It's not what I want. Yep, just give this the same name, but with preview at the end. That's my name convention there. And then just copy this into here. Okay. So what that does is now if I go to my all sources, you can see I have this information here. COMP108 lecture 2. Yeah, very cool. Got a published date and everything. Don't know why these are lacking images. I guess I just didn't add them yet. But I will come back to those. But yeah, the rest of these do have images. So, COMP108 lecture 2. Right. So first one, what is an algorithm, right? Jeez, right. Let me swap this actually with Claude. It's easier to get to. Right. So an algorithm. Okay, I'm lagging already. Not sure why. An algorithm, well, because I'm streaming, right? OBS, is according to the definition, it is a sequence of precise and concise instructions that guide you or a computer to solve a specific problem in a finite amount of time. Right? So finite is, I guess, the key word here. So it's a sequence of precise and concise instructions that guide an agent to solve a specific problem in a finite amount of time. And here we have precise and concise in bold, specific problem in a finite amount of time. Now obviously I'm not really paraphrasing here, but whatever. This is the definition that's given. Input, algorithm, output. So yeah, so you have an input, you feed it to an algorithm, and it produces an output. Kind of like a function, I guess, is what I kind of equated it to. And then the difference between algorithms and programs. Right, yeah, so algorithms are algorithms versus programs. What is, whoa, that's big. What is an algorithm? So, yeah, so from what I understand, an algorithm is, like, how it's written doesn't matter, whereas programs where, like, the form does matter. So, an algorithm, is defined by its instructions and not by instructions regardless of its form. The same algorithm can be written in pseudocode and Python and C++ and Zig, right? Pseudocode. After dictionary. Zig as well. And Zig. The form is different, but the instructions are ultimately the same, right? In contrast, right, a program is tied to its syntax, right? So like that's how we have like a C++ program, right? That's like saying a C++ program is different from like a C++ algorithm, right? A C++ program differs from a Rust program, even if what they do is even if the machine code they produce is identical. Yeah, so that's the idea there. Maybe you can disagree, but that is the definition that's given in the course. I would not be surprised if I got a question like that in the exam. Then we go into pseudocode, right? Although there's an example here in the slides. Which actually I will include. For example, consider the following algorithm. Set a temporary variable p to 1. Repeat the multiplication p equals p times x, or rather like p stores p times x n times, and then output the results of p, right? So it's algorithm to compute the nth power of a given x. So the idea here is that in different languages you can write the same thing. So this algorithm is implemented differently across different languages. So like in C++, for instance, you have well, this code's kind of incorrect. Like you could just p equals 1 unless it's really predefined, I guess, but this is what power, right? So we do int p equals 1. Okay, what? Compute the nth power of a given x. Like 5 to the power of 6. Oh, I see. It's like 5 times 5 times 5. Yeah. So like this, and then you can do 4. Int I equals actually this isn't even well. Okay, I is less than n I plus plus. P equals p times x, and then just return p. Or it says, well, it says print, I guess. So let's say print the result of p. So then we'll say standard print line using the new syntax p, right? Or in Rust, exercise here, we'll do like let p u32 equals 1. Mutable p, sorry. I mean, this is just one way to do it, obviously, but for I in 0 to n, I believe that's correct, p equals p times x, right? And then print line like that, p. I think this is correct. Just check that. Rust for loop. I mean, I shouldn't get lost in the semantics here, but for x in array.len, yeah, that looks right. Rust print line. Yeah, I believe this is correct. Or another example from, let's do Pascal. That's given there. We'll do Python. P equals 1 for I in range of n. Just P equals P times X, and then print P. Holy moly, look at Python Go. World's easiest language. And then, but we can, so to have it be, so to have the code, so to have the algorithm be represented in a way that isn't tied to any particular programming language, we can use pseudocode. And pseudocode is non-specific, right? So, for example, we may want to do P stored in 1. So 1 stored in P for I 1 to n. P stores P times X, and then we output or print P, right? Now this is arbitrary, but let me just have a look if it says that in the slides well. Yeah, so pseudocode is similar to a programming language, but is more like English. But is also more similar to plain, well, not to plain English, but similar to English. But it's also closer to plain English, with readability being key. Right? So well, not key, but with aiming to be more human readable, let's say. Okay. Yep, so there are pseudocode conventions, but ultimately there is no one uniform grammar that must be followed. And I know this because I learned pseudocode in like GCSE, and now here, and other places too, and they all differ. Although it's annoying because in GCSE you're expected to learn a particular type of pseudocode, even though that's not how pseudocode works, but okay. Yeah. So, okay. So let me copy this code here. So in COMP108, pseudocode is written like this. Boom, boom, like that. Kind of funky, but honestly not terrible. I need to figure out how to get special symbols on my keyboard, like arrows and stuff. Just replace them for now. Right, so yep, no. I mean the downside is no syntax highlighting. So honestly, like if I was doing pseudocode, I'd probably just use like Python or something, or like Rust. But anyway, trace table, how variables change. Right, so there's also trace tables. It's quite important. I feel like yeah. So let me break this out here by doing pseudocode. Right, pseudocode. What does pseudocode actually mean? Pseudo means like... Pseudo is an adjective or prefix meaning fake, spurious, or not genuine. Right. Pseudo means fake or ingenuine in English. Right, so generally. So then you got trace tables, so trace tables. A trace table is a way to track how variables change throughout an algorithm's, I guess, like iteration steps. So, for example, well, I'll take a screenshot. I can't be asked to actually make a table. So let's do print screen. From the above algorithm, so yeah, so the trace table for the above algorithm is, I think I can actually just link to it here. Oopsie. Hashtag, whoops. In comp, how do I link to a particular text block? I can't remember now. Let me just remind myself here. Oh, that's right. It's an uptick, a caret, like this. There you go. So I can just link there. Right, so yeah, so that's the trace table. Right. And there's another example, but you can just skip that. But like, you might get a question that's like, how do I, like what is this algorithm doing, right? And the one given is highest common factor, apparently. That's the example. Yeah. So just have like an important note here. Even in pseudocode. Okay, well, this course opts to use the %sign for the modulo operator. Like many popular programming languages do. Just important to know. Maybe like a warning even. But yeah, I mean, whenever you see a %sign, there's very little else it can mean. Like if it's used, you can assume it's modulo, unless it's being used like on a number, obviously, like 100%. The use of a Boolean variable to mark a significant event is called a flag variable. It is recommended that you draw a trace table to find logical errors. Okay. Trace tables can both help catch bugs / logical errors, and also to figure out what an algorithm actually does. Does it even mention flag variables in the slides, or was that added later? Maybe it was like mid-lecture they mentioned it. By the way, I don't know who made this this website. I guess it was Ben Weston, but like, goddamn, that is dedication. W. Ben Weston. Anyway, these would be a variable to mark a significant event. It's called a flag variable. You can use this to mark a condition that has been met. All right. A Boolean variable that is used to flag an event is fittingly called a flag variable, right? Important, I guess. Okay, and that's it. That's lecture 1 done. I mean, very simple, you know. It's like literally the first lecture, but quite cool. So I'm gonna move these now to this other screen so I can access them more easily, but not much to see there. So then there's pseudocode part 2. And tell you what, I'll finish. Should I finish this slide? I'm trying to think how I should do this. I guess I should finish both parts before making notes on it, like atomic notes on it, just so I can like finish it. Because like these were literally days apart. Like one was 29th and the next one was the 30th. So yeah, I'll go to the next one. So we got pseudocode 1 and pseudocode 2. These are the sections, right? Yeah. So pseudocode 2. Very little even happened here. In fact, is it literally just examples of pseudocode? Okay, how to write it. Yeah, it's just an exercise of how to write pseudocode. So actually you could just skip that one. Okay, fine then. That one wasn't even particularly important. In that case, just skip that one. Don't need to mention it at all. In the same way I skipped number 1. And yeah, so let's make some notes from this. So first of all, what is an algorithm, right? An algorithm is a sequence of precise and concise instructions that guide an agent to solve a specific problem in a finite amount of time. So precise and concise is important here, right? So an algorithm is a set of precise, concise instructions that can be fed to an agent, whether that be a human or a machine, to what? I mean, like to carry out a task, right? Well, okay, so to solve a specific problem is quite important in a finite amount of time. yeah, these two are quite important. So it's a specific problem and it's in a finite amount of time. If an algorithm takes an infinite amount of time, then it's not so useful. I'm guessing. At least that's what it says here. Topics here would be algorithms. Yeah, algorithms. Yep. So anything else on that? No. So algorithms. So algorithms are. An algorithm is a set of instructions to solve a specific problem. Sources, we can link to COMP108 lecture 2, right? And to a particular section. What is an algorithm? Or rather, this particular part of it. So then you can see there. And since this is a direct quotation, I will actually mark it as a quote. Oopsie daisy. And call it. Actually, I'm going to put it on the same line here. There you go. That is an algorithm. Huh, interesting. Oh no, it does. It puts a thing here. Okay. Right. So that's one note right there. That's one note right there. Next, an algorithm is defined by its instructions regardless of its form. The same algorithm can be written in pseudocode and Python, supposed in Zig. The form is different. So, yeah. So an algorithm. Link it to there. So Jesus Christ, an algorithm differs from a program in that a program is tied to specific syntax, a specific programming language like C++, Rust, Python, etc. Whereas an algorithm is defined by its instructions and not by its form. And then I will include this exact example. Therefore, it is often best to it is common to instead represent an algorithm in pseudocode, so that it can translate to any language. And here I'll actually wrap these. Misclick. There you go. Yes, this is COMP108 lecture 2 # what is an algorithm? No. Algorithms are programs, that's right. Right, so there we go. There we go. What? What? You spent £12 at Amazon Music? Fucking when? Hello? Hold on, chat. Sorry. What the fuck? And I use Amazon Music. For fuck's sake. My own passwords, don't remember it apparently. Ay. Okay, hold on. Let's sort this out now. Maybe like my sister or something. That's weird though. Why would my card even be available? Oh my god! I used the wrong symbol. Oh fuck's sake. Okay, whatever. I'm not just messed up my Amazon password, but whatever. I guess I just have to remember. Why the fuck? Can I skip this? No. Okay, I don't listen to any of these guys. Fucking, I don't know. Michael Jackson, David Guetta, and Coldplay, sure. Gonna ask my parents about this. Ooh, I don't care, bro. Show me my account. Yeah, so my account doesn't have Amazon Music. So someone's just used my card to buy it. Could be my mum, but like I added my shopping to the profile. Yeah, I added my card to my mum's account, so that's probably it. Okay, well I've asked in the group chat, so hopefully they get back to me on that. At least I know I haven't been hacked. My account has been compromised, but that is bizarre. It's weird too, because like, it should really ask for my verification before doing something like that. Like Revolut should ask me, pending, reverted on the 22nd of May if unclaimed by a merchant. Okay, so it'll be cancelled later. Okay, anyway, what the hell? That is just funky. Let's go back. Right. So, yep, this, right? So, a program is tied to syntax, but an algorithm is just its instructions. Abstract. Again, algorithms. And then the other one what is pseudocode, right? So pseudocode is a way of writing code that isn't tied to any particular programming language. And does not have a universal, uniform, universally agreed upon grammar. It aims to be more similar to, it also aims to be more human readable than traditional programming languages. See if we have any examples here. For example, actually just put a fucking example thing here. Example pseudocode from COMP108. Sources COMP108 lecture 2 hashtag pseudocode. Okay, so pseudocode isn't tied to any particular programming language. Topics here will be, I guess, just programming. I don't need a whole topic on pseudocode. Okay, and then here I can also link to this post, this note, this atom. What? Okay. Cool. I can't scroll for some reason. The hell? My mouse works. Okay, now I can scroll. Right, must be a bug. Cool. Cool. Close those. Trace table. Yeah, so trace tables can track alphabet change trace steps. So we can note here, based on the most important information. A trace table can be used to find bugs in an algorithm, bugs and logical errors in an algorithm. And can also just generally help with figuring out what an algorithm even does. So I use this. So like example, trace table for an algorithm that calculates the nth power of an integer, of a number. That's not what that is it? No, sorry, this is the sum. that calculates the sum of natural numbers up to n. So if n equals 4, you get 1 plus 2 plus 3 plus 4, which gives you 1 plus 3, 6, 10, right? Yeah, looks good. So sources, again, COMP108, lecture 2, hashtag trace tables. This would fall over under algorithms. Yeah, so a trace table is useful for finding bugs in an algorithm. Cool. Then we have these two notes here. So the bump operator, %, is often used in programming to represent modulo. Modulo, also known as, well, okay, which calculates the remainder from division. Now, this isn't actually really true. Often it's something else, but like, how to say it? In C++, well, okay, in C, for instance, in C languages, it actually does something else. So is modulo in C true modulo? It's not. It gives the remainder. True modulo should always be positive and be in the range from 0 to a number. The remainder is slightly different. So, hold on. Yeah, so -10 mod 3 is 2, right? But in C++ or C whatever, if you -10 modulo 3, or well, the percent sign 3 would actually give you well, you so yeah, -1. Yeah, that's right. Because it will divide by 3, -9, and then it'll go -1. Yeah. To represent remainder division, similar to modulo, but with an important difference. In some languages, like Python, let me actually confirm this. Python Playground. Actually, I should have Python on my system now. PY? Python? Okay. Python -10 modulo 3. Sick. Never mind then. I don't know how you do that. Python Playground. Ah, fuck that one. Is it not just like a uniform one? Whatever. Print -10 modulo 3, please. Should give 2. Yep, 2. So in Python, so in some languages like Python, this gives the true modulus, modulo, sorry. Whereas in other languages like C and like C, it gives it only gives the remainder. This distinction is important because -10 boom 3 equals -1, but -10 modulo 3 equals 2. Yeah. Lecture 2 hashtag this, but also from the one Reddit post I was just on, I guess. I only know this because I did Advent of Code, and I came across this issue, and I had no idea what was causing the issue, and this low-key set me back by like a long time, and that just completely just killed my motivation, but I did learn from it. Okay, I'm gonna go soon, so let me just wrap this up. Let me go one more anyway. Can I use this sign? Whatever, the percent sign operator is remainder, division, or modulo in programming languages. Yeah, in programming languages, yeah. So this would be in programming. Okay, and the final one is a Boolean variable that's used to flag an event is fittingly called a flag variable, right? So a flag variable is a Boolean that represents some change in state or the triggering of an event, effectively flagging that something has occurred. That's it. Very simple, but honestly, it took me quite a while to kind of register that. Like you see flags in files sometimes, in like file formats, to like say like, okay, like this, like usually Booleans are just called flags, like a language flag, whatever. Broadly speaking, flags don't have to be simple zero, simple true, false Booleans, but they are generally used in this way. Contradictory examples may be something like a language flag. What? Flags don't have to be simple true/false Booleans. Yeah, what? Why is that wrong? Dude, the fucking spell checker for Obsidian is horrendous, honestly. Worst thing in the world. This is in programming. Is it programming? It's also in just like data in general, like computer science. So I'm actually gonna just tag this as computer science, which is really broad. But anyway. Yep, so a flag variable flags a change in state. Or like flags. To be fair, a language flag is really not the correct way to use it. People could just call them flags. Boys begin. Well, yeah, flags are also sometimes used quite incorrectly to refer to just booleans or even enums sometimes. Enums, particularly in hex editing, right? But the semantic, but this isn't intuitive. Yeah. Okay. There you go. So that's that lecture done. That took about, well, less than an hour actually. Probably more like 50 minutes, maybe 45 given the detours we took there. And yeah, there you go. So this is found, I actually have no idea. Let's have a look here. Here we go. Pseudocode. Tied to this lecture here. We can see how these notes. Very cool. What are these tied to? Algorithms, which is a new category I made, and programming, which links to COMP108 makes sense. COMP108 is Java. Okay, so there you go. Now I should make some categories as well, like not these turn these into actual categories, but I'll do that later. Actually, I'll do it now as an example. So like for programming, okay, maybe not like that. It'll go here in maps. Yeah. And then you link the topics. So this will be programming. The topics will be multi-mathematics. Programming falls under computer science. Yep. And then if I go to my graph again, there it is. Okay, actually, how do I actually do this? Okay, let me delete this. But I'll go to my graph and I'll find it again here somewhere. Should be near coding. Yeah, I do have coding, by the way, which is different from programming. I might merge those, I guess. We'll see. Where is programming? 1.6 here. Algorithms, programming. There it is. Oh, right, because I created it. Right, so I just paste this here. Okay. And then, where is it? Here. Move file to maps. Cool, there are 14 linked mentions. This is these old. Okay, that's old. Whatever. Close that. So now, go back to graph view. That should be a category, which is this color. There we go. Programming. And you see it links to a few things. So for coding, I should probably merge those as well. So let me find that. Should be somewhere around here, I guess, would make sense. Definitely not the most efficient way to find things, but whatever. Here, coding. LLMs are great for statistical analysis of code. Reading code is at least as important as writing it. Programmers should write more to read less. A standard for styling code should cover the gaps of a compiler. Now, look, programming is like programming, like writing programs. Coding is writing code. That's why I have it as different. So I'm actually just going to leave that, because I do consider them to be two distinct different things. Anyway, that's that. So if I now look at my atoms here, wrong one, sorry, look at my sources, and I should probably pin this. Cool. This has bank links, which means it's being linked to, which is very well, it's what it should be. And yeah, I can later move on to the next lecture, which is algorithm efficiency, apparently. Is that right? Oh yeah, like bigger notation and stuff, which would be very good. Cool. So I'm gonna leave it there, and yeah, that's basically how my revision process is gonna go. There are also like quizzes and stuff which I'll do, and like practice questions. But the main thing really is just understanding the topics enough, and then I don't really need to do many practice questions because I just know it, right? Like content wise, which is really what exams should be testing. Unless you do like I don't know, like an engineering degree, where like you need to solve like hundreds of practice questions, so that when the time comes you can, I don't know, solve this engineering problem like mathematically. But like that's more building like mathematical skills, like testing your mathematical skills. It's just like understanding the concepts. That's not necessary. So, yeah, whatever. And like as far as, well, the good thing about me doing computer science is that I don't have to solve hundreds of math problems. For a lot of the cases, I should be able to get those, like the skills that I should be practicing is programming, and I already do that, so should be good. Anyway, subscribe.